You might need to configure Layer 3 VPNs in classic iOS or iOS XE. They're very similar. You could barely tell the difference. You'll recall from our previous Layer 3 VPN or one of my previous Layer 3 VPN videos, and if you haven't seen it, I'll put it in the cards up here or the comments below. Check that out. But this is going to be growing on that topology. So you're probably going to want to watch that first just to set the stage for what I'm about to do. I'm going to add a third PE to my previous 2 PE scenario. That previous one was iOS XR and Junos. So we're going to be adding an iOS XE PE node to our topology. Again, you may need to do that in classic iOS or iOS XE. They're very similar. And a long time ago, I enabled Layer 3 VPNs in the provider network where I work for the cable modem termination systems, CMTSs, the Cisco iOS XE CMTSs. It was originally iOS, then we moved to a newer CMTS, iOS XE, and it's very convenient. It's very nice to be able to bring MPLS into that CMTS. So you may need to do that, and here's how we're going to do it. Now, as a refresher and a reminder of where we left off in the previous videos, we have, for the SP core, we have router 1, 2, and 3 running Junos. Those are VMXs. Router 4, 5, and 6 are XRV9Ks running iOS XR. And router 7 down here is a CSR1000V running iOS XE. They've all been configured for an IGP OSPF, a simple single area, and the simplest of label distribution protocols for advertising IPv4 forward equivalence classes for the transit subnets as well as the loopbacks of all 7 routers, and that would be LDP. Again, please look at my previous Layer 3 VPN video where I showed Junos and XR configuration, and then a follow-on video to that, I spent a good amount of time diving into the verifications of everything. But just to refresh us on where we left off, we have CE1 and CE3. Those are this router and this router, just vanilla iOS. And CE1 is 1.2.3.2. CE3 is 2.4.6.2, and they can ping each other. Just do a trace route real quick, just to show that we are trace routing across the provider cloud. And here we are, router 1 Junos, router 4 XR, CE1, CE4, 1.2.3.0/24, 2.4.6.0/24. Now, when I add the next router, router 7, onto the edge of the SP cloud, this one is running XE, and I don't like where I'm going with this numbering, so I'm going to change our address space, okay, just to make it something that's simpler for this Layer 3 VPN. Okay, so this is what I'm changing it to. Customer 1, this is going to be customer 1 that is buying a Layer 3 VPN from us as the service provider, and we need to set that up. And we have 3 PEs on the edge of our SP core, and they're 3 different vendors or operating systems. We've already done Junos and XR, as I mentioned previously in another video. We're going to add XE in this video. So change the address space to something that looks nicer and easier to deal with. Customer 1's Layer 3 VPN is 192.168.1.0/24. That is the links that we are linking up with from PE to CE. So we're doing /30s, .0/30, .4/30, and .8/30. I stand corrected that this CE is CE3, as you can see in the picture. That was CE3. I had that mislabeled. That would be CE3. And so here we have router 7. It's our iOS XE router. We're going to connect CE5, and that's what we need to do. And I messed up there. You typically, by convention, use the lower IP address closer to the core or closer to the internet when providers are assigning IP addresses. And we're kind of going on the premise that this is our address space that we're using to link to a customer, us being the provider. So I would have usually used the lower number on the closer to the core. So that would be .1 and .2 on the customer, .5 and .6 on the customer, and then .9 and .10 out of that /30. And just so you don't miss out on any of the fun, here is the renumbering effort. First of all, the whole purpose of the lab is we're adding the CSR1000V as a PE. First, I wanted to change the address space. Here's what I did to router 1. I deleted and re-added the new address space. On the CE, I did the same. Then on, then I had to change the default route. Then on router 4, IOSXR, I removed the previous IP and added the new one. And then on customer edge 3, I renumbered it as well. We can verify. So we have 192.168.1.2 on CE1, 192.168.1.6 on CE3. Oops, we can ping across. Excuse me. And we can trace route through the SP core. Okay, now let's get down to it. Multi-protocol BGP. So we had to do multi-protocol BGP for VP to carry the VPN v4 address family between these in the previous video. But this is internal BGP, so the iBGP rules still exist for fully meshing your iBGP environment between all of your iBGP speakers. Of course, it's MP-iBGP, multi-protocol iBGP in this case, but it's still iBGP. So we're not going to do route reflectors. I'm going to show a scaling of the interior BGP protocol later when we do a route reflector configuration, as well as a dual route reflector configuration to remove the single point of failure that a route reflector creates. And so I'll probably show that with Junos and XR, two different route reflectors, the same route reflector dual cluster, providing redundancy in the SP core using Junos and XR, two different vendors cooperating together. So that'll be really nice. But in the meantime, we're going to go with the more burdensome but commonly used fully meshing of iBGP. The formula is n times n minus 1 divided by 2. N being the amount of nodes. We have 3 nodes. 3 times 3 minus 1. 3 minus 1 is 2 divided by 2. So this is 6 divided by 2 equals 3, which means that's the full mesh rule. So as you have more nodes in your service provider core, you have more touch points, more chance for typo errors, more chance for just problems. That's where route reflectors and dual route reflector clusters come in very handy for redundancy and for actually making the configuration much simpler on the PEs as well. But until then, we're not going to do that right now, but we're just going to do a regular iBGP configuration. We already have iBGP from here to here. We need to configure iBGP from here to here and also from here to here. This is our 3 connections, 1, 2, 3. So fully meshed, everybody's talking to everybody. And so we need to add these 2, which means we have to fully configure 2 neighbors on this one, but then we have to go back to this router and add a neighbor, and go back to this router and add a neighbor also. So here is our multi-protocol BGP foundational configuration that we need to put in place for iOS XE. I hope you can see that. Okay, so our AS is 64512. We have a private AS number that we've been using. Again, if you saw that previous video, you would be up to speed on that. And so we create the BGP process with the local AS number. We give it a router ID, and we turn on no BGP default IPv4 unicast so that it doesn't start adding the IPv4 unicast address family to every neighbor. We're not using BGP for vanilla IPv4 prefixes through the core. We're using it for VPN v4, for layer 3 VPNs. It's carrying IPv4 prefixes, but the address family is VPN v4, where it adds a 64-bit route distinguisher, prepins it to the 32-bit IPv4 prefix. That 96 bits forms the VPN v4 address family, and so that's exactly what v4 layer 3 VPNs is all about. So we're not turning up BGP for IPv4 unicast, we're turning it up for VPN v4. So by turning off the default behavior, it stops BGP from trying to add a IPv4 address family to every neighbor you create. All right, and you'll see that in a moment. You need to globally configure your neighbors. So here we are in router 7, the iOS XE box. We got a neighbor back to router 1, we got a neighbor back to router 4. All right. Then you drop into the VPN v4 address family, and you have to activate those neighbors as well, and you have to extend the extended community attribute. The extended community attribute is absolutely the route target. All right, so that's pretty much it for the foundational configuration for multi-protocol BGP. And let's put that in place. And what I meant by the extended community attribute is absolutely the route target, is that it's the capability to send the route target. I haven't even shown the route target yet, but when we configure the route target, you need to be able to send it using this configuration command. So we're just setting up the ability to send RTs. We haven't configured the RTs yet. Okay, let's put this configuration in place. Copy that, drop it into router 7. There we go. Show BGP summary. Show BGP summary. Oh, excuse me. All summary? Or all summary. There we go. So you can see we're getting some messages, interestingly, from Junos, but we're not getting them from iOS XR that I can see. So 10.10.01 is sending us messages. Where is it? Yeah, router 1, Junos, but we're not getting any messages from iOS XR right away. Anyway, we haven't configured the other side, so let's do that. Okay, of course, BGP neighbors need to be configured from both sides, and so we need to fully mesh it with our 2 previously existing boxes. Here's how we do it in Junos, and so we'll do this on router 1. Okay, show BGP summary. It's active to .7. Oh, established. There we go, that fast. It was active. Now it's established. And let's go back over to our iOS XE box, and there we go. 10.10.01 is up. Let's look at that. All right, so that one's up. So now we got to do XR. Here's our XR configuration. We're adding a neighbor. And let's put that in place on router 4. Show BGP summary. Is it all summary? All summary? That's one way to see it. .7, we're in connect state. There we go. We went from connect to now we are established with no prefixes being received yet because we haven't set up the PECE configuration on router 7 yet. And there's our message. 10.10.04 is now up. There we go. They are both up. Here's another way to verify that in iOS XE. Show BGP VPN v4 unicast all summary. This way you're only seeing neighbors that have the VPN v4 unicast family configured on them, and then these are the two neighbors that do in fact have that VPN v4 family. Here's a way to verify that. Show BGP VPN v4 unicast all neighbors and look for that specific neighbor. If you pipe include address, it'll tell you that the VPN v4 unicast address family is being advertised as well as received. So this is really good in troubleshooting any kind of problem, that you do in fact receive the capability from the far side neighbor to be able to send and receive the VPN v4 address family for that neighbor. That's router 1, and here's router 4, and we see the same thing. We are advertising as well as receiving the VPN v4 unicast address family capability. Okay, at this point, we've just done core configuration or foundational configuration that's not specific to any VPN. As I explained in the previous video, there's foundational items that need to be configured in a provider network. The IGP, the label distribution mechanism, whether it's RSVP-TE or segment routing MPLS, or in this case, label distribution protocol. And then BGP, multi-protocol BGP, and the address family component, VPN v4, as we just saw. All that is not specific to any customer VRF. Now we're going to get into the per customer specific configurations, all right? So as I just mentioned, R7 now has the fully meshed neighbors. It's advertising the capability to do VPN v4, but we've done nothing from the PE to the CE component of the VPN. This is where you get specific to that customer. And it would be the same if I drew another customer here, and a third customer, and a fourth customer. All those things could ride over all the non-customer specific configurations that are now in place. You don't have to turn up new multi-protocol BGP foundational items or LDP or IGP stuff in the core. It's kind of like the underlay. You've turned up the underlay, you've got the foundational BGP component, you're advertising the capability to do VPN v4, and I'm just re-emphasizing, so that you can now do the overlay L3VPN per customer VRF stuff. All right, so let's get into that. Okay, let's configure the actual VRF per customer configurations on router 7 now. This is configuring the VRF itself and adding a route distinguisher and an import and export route target. This is configuring the PE to CE connectivity from port 3 down to fast Ethernet 00 on the customer edge router. This binds those together. It goes into BGP, goes into the address family VRF1, IPv4 VRF1 address family, and then we redistribute that subnet between these two routers. That's all we're doing at this point, is redistributing that /30, and then we exit out. Then we'll go over to the CE and configure the CE as well. All right, here's our customer edge configuration. Simply fast Ethernet 00, an IP address 1.10/30, a default route to 192.168.1.9, which would be default routing up to router 7. Okay, I put that config into the customer edge, and I'm pinging 1.9, which is the interface on router 7. So I'll put the VRF config in place on router 7. Currently, show VRF is nothing. Show IP VRF. So let's configure the VRF. Okay, now we have a VRF config, but you see there's no interface attached to the VRF yet. Let's go back and add that interface now. Interface 3. Might need to no shut it. Okay, and add .9, and let's see if that interface starts pinging back there in the background from the customer edge router. Should start pinging any second now. And any second now. Let's see what it looks like. The port is in there. And just waiting for, I don't know if I no shut the fast Ethernet port. No, I didn't. So let's do that. Yeah, I didn't do that. Now, let's see if we can ping. There we go. Okay, good. So we're pinging from customer edge to provider edge, right? And so what I'll do is I'll start up a ping to 1.1, which is, 1.2, which is customer edge 1 up there off of PE router 1. So let's put that in place so that when we bind the VRF into multi-protocol BGP, we should see some action. So let's put that in place. There we go. See those pings start? We're good to go. So now this router can ping 1.2. It can ping 1.6. We can trace route to both. Very good. So we're trace routing across the SP core. And I could speed that up. Just probe one time per hop. So we're pinging CE1, or trace routing. We're trace routing to CE3. And we are good to go. So let's verify a few things real quick. Now we saw from CE to CE, connectivity is good. So we have a good customer experience at this point, but let's verify a few things. On router 7, if we look at show BGP VPN v4 unicast, we see that we're receiving the 1.0/30 subnet from that next hop, that protocol next hop across the provider core 10.10.0.1. We're receiving 1.4 from router 4's loopback. And if we look in the rib, show IP route VRF1, we see that we have that same information, 1.0/30, 1.4/30 via those BGP peers, all right? If we look in the CIF table, the Cisco Express forwarding table that shows us the fib, we look at it per VRF, show IP-ceph VRF1, and we look for that subnet 1.0/30. We have a label 24004 and label 16, and the other subnet going towards CE3 is only a label 24011. Now, if we look in the lfib, show MPLS forwarding, we see that in order to get to router 1, 24004 is our outgoing label to get to the loopback of router 1, okay, 10.10.0.1. To get to router 4, where customer edge 3 is hanging off of 10.10.0.4, our outgoing label is actually a POP label, and that's because from router 7 going over to router 4, we're the second to the last hop. This is known as PHP, penultimate hop popping, and you get a implicit null label advertisement from that last hop to go ahead and pop the label before you send that traffic. So in a VPN, you have two labels. So this router, router 7, is popping the core transport label so that when it forwards that traffic to that ultimate hop, it then only has the VPN label. So we can see that in that case, let's stay on subject with the customer edge 3 subnet for router 4. The only label we have remaining is 24011. So let's go over to router 4, and if we look in the lfib there, show MPLS forwarding, we see that 24011 is in fact the aggregate label for the per-vrf VPN 1. Okay, so that is what is signaled over to router 7 as the bottom of stack label, otherwise known as the service VPN label. Now let's go back to the subject of router 1 over here for customer edge 1. We have a couple hops. We have 1, 2 hops before we get to the last and final hop of router 1. So there is no PHP for this router. R6 would be the penultimate hop for that traffic going that way. So if we look at router 7, for that subnet, we have a label of 24004, then a label 16 is the bottom of stack label. 24004 is in fact the outgoing label of how to get to router 1, and router 16 is the VPN service label at this point. If we go to router 1 and we look at the lfib here in Juno's show route table mpls.0 protocol VPN is a way of seeing only your VPN labels inside your lfib, and we see that yes, in fact, label number 16 is in fact the VPN label for the label switched interface of VRF, otherwise known as routing instance in Junos, routing instance 1. All right, and so that's how that traffic gets forwarded. That was kind of funny whenever I was showing the bottom label here, I said router 16. I meant label 16, obviously. All right, great. We now have a functioning layer 3 VPN with 3 sites, CE1, CE3, and CE5 going through router 1, 4, and 7, Junos, XR, and iOS XE. As we see on the board here, this is how it's being done. This subnet and this subnet and this subnet for all those customer edge routers are able to communicate with one another. Hey, that's it. We're all done. We've added iOS XE to the layer 3 VPN. We've got 3 customers talking. This is cool. We got 3 different PEs, different vendors or different operating systems. So this is great. I hope this is coming in handy to you in your job, in your pursuit of certification, whether it's Juniper or Cisco. Give me a like, subscribe, and turn on notifications, and you'll get updates when I upload new videos. Share this with someone else in your industry, in your job, another colleague that you think could benefit from this. And I look forward to the next video. Thank you.